Let's talk a little bit more about specific design of the process in Unix. Okay. Process is, in Unix system, process is represented by some kernel object, as I told you before. And this object have a unique ID, and we call that ID PID, process ID, process identifier. Okay, okay, that is good. And interesting thing is that in Unix, in order to manage multiple process, they use hierarchy. They make some hierarchy among the process. By how? So when you want to create a new process, it should be created by another process. This is the rule. You cannot make a process from scratch. When you want to create a process, it should be spawned from existing one. It's like a human. So we are designed in a way that if a new human needs to be created, it should be, you need to have a birth from your parents. This is how man is intended to be created, according to the Bible. Did you know that? Where will be the starting point? I mean, if all processes are created like that, then it will form a tree, because there is a parent and child relation between among the processes, right? So it will form a tree. Then which one will be a root? Root가 있어야겠죠. Then what? Root will be a process that will be created especially when system starts. And usually in Unix system, that is coded as a initd. Heard of it? Or systemd. initd라고 들어봤어요? initd or systemd. systemd. And they are usually have a PID1 because they are the beginning point of the process. These are kind of special because they do not have any parent, but it's initiated by the kernel when system is boot and up. And so you had a question?
I have a question about root.
About a root. Okay, root is for the PID1, and once you check in a system, you will see that they always have an initd, and from the initd, so every process is ultimately ancestor of initd. That's how Unix operate and manage the processes. So is this the only way to manage the processes? No. Maybe depending on an operating system, they have a different strategy for managing the processes. But this is how Unix works. But and also this is a kind of a good idea, good design. So almost all operating systems take the same idea. Why this is good is that the reason why this is good is that basically in Unix, parent process, child process relationship mimics the relationship between caller function and callee function. That's basic intention here. So as a caller function, call another function and make it callee for the same manner or similar manner, parent process spawn a child process to delegate its subtask. Spawn means create and start. Create and start. It's different from the function call in a sense that in a function call, we have a single control flow. And upon the control flow, caller function bring the execution of the code of the callee function and run some instruction of the callee function. And when it's done, it takes the return value back. That's how caller-callee relation happens. Still single control flow. But in parent process and child process, a new control flow is created. So parent process and child process run concurrently. Basically, they run concurrently. But initial purpose of the child and parent relationship is that multiprocessing. Multiprocessing means that a program having multiple children processes. So multiprocessing that originally demanded in order to parallelize a task. Parallelize task means that distribute the work to the multiple instances of the processes, so to accelerate the computation. That's initial purpose of the multiprocessing. So as a saying similar to caller function, delegate work, some subtask to the callee function, parents process delegate work to a child process. So that's the reason why people find this tree structure is a kind of good idea in managing the multiple processes. So I think I explained most of them. So if there are a parent process, so for example, parent process here, we have a parent process, and it might have for example, this amount of the data. Parent process might have this amount of data, and what parent process is needed, parent process need to process all this data. So one possible idea is that parent process spawn multiple children processes. Multiple children processes and assign them a subtask. You do this job, you take this job, you take this job, you take this job, and you take this job. Okay. And if you finish on this job, please send the result back to me. So parent process wait until all children process finish their job, then get the data back, and parent process summarize the result and return the total result back to the user. That's the initial purpose of the multi-processing. Okay, that's the reason why this tree structure makes sense. And in order to do so, parent process can wait until children process to finish its job. And parent process have a different mechanism to control the execution of each child process. Not only the mechanism, but also it has authority to control the children process. For example, parent process can kill the child process. Kill here means terminate, finish its execution, even before its own termination of the execution. 중간에 죽일 수도 있어요. Or make some synchronization with the child process. And operating system provides some features that make a parent process easily exchange data, transfer data to the child process, and also get the data back to the parent process. Operating system provides a different channel for such a parent-child communication. Okay? And you will learn there are those features, and I'm explaining this because this is the initial intention for multiprocessing. But the truth is that multiprocessing is not only used for this type of the parallelization. Multiprocessing can be used for different purpose. But we are using some mechanism prepared for this initial purpose. Okay. 그래서 좀 설명해 주는 겁니다. For example, the system API that create a new process is called as a fork. It's weird. Why it is a create a process or start the process, but it's named as a fork. 이상하죠? Why? This structure looks like a fork. And another interesting is that when a parent process create a child process, parent process copy or its memory state to the child process. Why? Many computation steps are needed for that copy. But why copies are needed? Because initially it is intended so. So it's a similar idea that callee function can access all the global data that has been manipulated by the caller function. For the same reason, we transfer all the current state of the computation to the child process so that it can continue some of its subtasks. So for that per se, at the fork, all the all the data stored in the memory of the parent processes are exactly copied to the memory space of a child process. That's the reason for such behavior of the fork system call. Question?
We have a question on Slack.
Uh,
Ayabin asks, if the snapshot of the state is stored for every process, wouldn't it use up a lot of additional memory space?
that's true. That's true, but how? Because it is you who command the computer to do so. So if you open up so much application, OS will reject opening up a new process. So this is an example, typical snapshot of the tree structure of the processes in a Linux system. So the highest ancestor is an init, special one. And init is for what? Init is for executing some, is to launch some system programs, daemons. So in your configuration of an operating system, you can define a set of the program that needs to be executed as soon as system starts. And init read those configuration and start those daemon programs, including, typically it includes SSH daemon. What that daemon is the program that answers to the SSH request. For example, if you turn on a booty and try to make a connection through the SSH, then this daemon is responding. And how? So if we establish a new connection with some client, you guys are client, the one that access from remote, then it's bound a child process. And this child process is delegated for making a communication with some client. And upon that, inside this program, if you command to open up a batch, so after establishing a connection, what it does is that this process become an agent for a remote user. So it spawn bash or kind of a shell program. So if you type on through the booty, those commands will be received by this shell program. And if you launch a program like a a.out, then this one make a fork and execute the a.out. Yeah, I think I have a kind of this type of thing at the video lecture as well, right? I show you the process tree, PS tree, and show you different type of the process that are actually running on a P server, and give you kind of a explanation on this part as well. When you launch a program, you give a bash the path of a executable file, right? What it means, load the binary represented in this file, load this data and encode in this file to the memory and start execution, right? That's how it works. And there are other demos as well. Continue, okay. So life cycle of a process. So once it got created, yeah, what it does is execute the instruction in sequence until it reaches to the termination instruction. That's the life cycle for the process. So initially, once a program got executed, got created, it start from the ready state. Ready state means that, okay, things are ready for execution, but initially this process does not have a CPU. It doesn't give on a CPU. Then how? Then what? Everything is prepared, but it's not yet dispatched to a CPU. So it's not actually make a progress in its execution. Then operating system, more specifically, scheduler, decide that, okay, this process, this is a turn to execute this program, or more strictly speaking, this is a turn to make a progress for this process. Then it goes to the running state, and the context prepared for this process will be dispatched. So all the registers values for this program will be given to the CPU register, and then make a execution. Then CPU automatically load the data instruction and make a progress on this process. So running for a while. And there are two cases when running states get transited. First case is that if this program try to invoke an IO operation that requires waiting for some IO event to be completed, then automatically operating system recognize that waiting and turn the process into blocked state. Why? Because for the moment for the waiting, this process does not need a CPU. If a CPU is given, those time will be wasted. Why? It's not necessarily we need to wait for IO things to be completed, right? So automatically this returns to the block state. And when IO is done, this can be easily recognized by operating system kernel why IO is managed by operating system kernel. So when IO is done, then operating system restore the state of the process to the ready state, which means that I'm ready for taking a CPU. If you assign me a CPU, then I will make a progress. But this needs to, this process cannot immediately take the control of the CPU, but needs to be waited. Why? Because there are many other processes that are running as well. Okay, that's first scenario. Second scenario is that for a certain amount of time, if it doesn't have any IO, then it continuously contain the CPU, but operating system recognize that, okay, you take too much time, your time is up. Then operating system regain the control from the currently running process. This step is called as a preemption, which means that context switching is intentionally happen for time sharing. But the problem is that, okay, if a CPU, a certain code is given to the CPU, then the next instruction to execute is fully determined by previous execution, previous instruction, right? As a result of the previous instruction, next instruction to be executed will be determined. And all things goes automatically once program is executed by CPU. CPU automatically load instruction, next instruction, and the control flow goes really quickly. Then how can we stop the execution from this CPU cycle? Cycle of the patch, decode, execute, patch, decode, execute. How can we stop this cycle? Yes, interrupt. Interrupt mechanism of the computer architecture provide independent control flow, right? So when interrupt signal is given to the computer, then before patching the next instruction, what happened? Computer architecture load interrupt handler code and handle that interrupt handler code before continuing its execution. In that sense, interrupt is what? Exception. It raises an exception of the control flow, right? We have that mechanism for asynchronous communication between CPU and IO devices originally. And computer operating system is exploiting that mechanism to implement time sharing, which means that if computer architecture does not provide interrupt mechanism, I think time sharing is really hard to implement or impossible to implement. Do you see my point? Interrupts are needed to preempt the current context of the CPU. Okay. In your textbook, this step is called as a deschedule. Deschedule here means that, okay, your time is up and OS is taking the control back. And the OS determine, okay, who is the next? So there will be multiple ready process. So there are multiple processes waiting for have a chance to take a CPU control. The OS give another, OS dispatch another process, another ready process on the CPU. And for like after like 1 minute or after 1 sec, another interrupt happens and CPU regain the control and decide the next process to execute. So to distribute the time over multiple ready processes. That's how time sharing happens. Okay, So the piece of the code for doing that job is coded as a CPU scheduler. So CPU scheduler make a decision for process state transition, whether running state is going to ready or running state stay as a running or running state go back to the block or something like that. All those things are managed by operating system. This is another depiction of the life cycle of the process. I take it from the old textbook because this one is a more accurate than your textbook version. Your textbook version is kind of simplified one in a sense that your textbook version does not have a new state and terminated states, but it is more accurate to have a new state and terminate states. New state, at the new state, what it does is that still not programmed. The target program is not loaded. You can think about a lifetime of the process before main function is executed. Even before main function got executed, process get a burst. And operating system, I told you that operating system execute what? Small program do the preparation stuff that is called as a loader. loader라는 거 부른다 그랬죠. That is also widely used system program that run on an application layer that become kind of a launch rocket for target program. So you prepare all those initial steps, and then it invoke a main function. So there are stages for that stuff. So at the new state, it do the basic steps and allocate resources, and everything got prepared. Then it switch to the ready state to get a chance for real execution. And then three states are basically the same. Sometimes productive state is referred as waiting. And when it reaches to the exit, which is the end point of the main function, or if a program execute exit function, exit이란 거 알죠? Exit. There are some remaining things to do in operating system per se, or in operating system per side. So it doesn't terminate immediately, but it needs to do some all the tearing down instructions. All the tearing down steps are remained. And so there is a stage called terminated. So target program is terminated, but for operating system's job, it needs to go to the terminate state and do the remaining stuff. One of the example for the remaining stuff is that for child process, if it is to program to make a synchronization with the parent process, for example, parent process is a program that it waits for every child process to get terminated. Then child process needs to make a communication with the parent process to notify that this one is going to that. Those things are remained. So process temporarily goes to the terminate state and then finishes, get fully removed. One interesting phenomenon is that parent process is programmed in a way that it makes a synchronization with the child process when child process is terminated. So parent process is waiting for the completion of the child process, which means that child process is obligated to send the message to parent process when it gets terminated. But what happens to another, parent process may be gone before child process's termination. 근데 it's a sad story. Sad story is that this child wait for parent process indefinitely, but parent process cannot answer on that communication request. It's kind of sad story, right? Then this child process, although it finishes its job, but cannot fully finish its termination step. Then what? This child process become zombie. Yeah, such child process is called as zombie process, and cannot finish its execution so that it cannot release all the resources that has acquired. So this is it's kind of due to the program bug or system trouble. But if your system have a lot of a zombie process, then many resources are now wasted. So time to time, administrator check that whether such zombie exists and needs to kill them. But those killings should be carefully done because there is some reason behind for such an indefinite wait. So this is a kind of kind of a failure, the failure of the program execution. You'll see that they are represented as a zombie process when you check the status of the process. So this is a typical example of the flow of the program execution. So process 0 is running, and process 1 is sitting in a ready state. So both of them have ability to execute, ability to make a progress when they are dispatched to the CPU. But in this system, only one CPU exists. So only process 0 is running. And if process 0 is done, so for example, if it is terminate, then it is very obvious that process 1 is now running. Okay, that's one good scenario. Or process 0 is first occupying CPU, and then it goes to the IO and it goes to the block. Then what? There is no need to allocate a CPU for this process 0 blocked process. So CPU is dispatched to process number 1. Then from ready state, process 1 make a transition to running states and make a continuation in execution. And at this moment, the IO is done. Then as it is acknowledged by IO devices, operating system bring the process 0 back to the ready queue. And at this moment, when the process number 1 is done, then the scheduler will pick another ready process in ready queue, and there are process 0, so it occupies the CPU and continues execution. That's another, that's one valid scenario. Are there any others? Okay. Okay. Yeah, before explaining this stuff, let me explaining about, okay, let me explain, okay. So thinking about that, here we are running a certain process for a while, and then here we kind of stop execution and make a context switching to another process. In order to make this happen, we need to store the snapshot of the current execution, right? And how those snapshots are taken and where it is stored. They are actually stored in kernel space. The truth is that memory space is managed by independently. So whenever a process holds a memory location, then operating system do not really reclaim it until the process will be terminated. It will be maintained as it is. But important thing is the process state, the state of the CPU. So these should be preempted, right? Because another process should be dispatched to this current CPU. So we need to store the data. Where? So in the kernel, under the kernel, we have a structure called process control block. Process control block. You can think of it as a memory snapshot of the CPU. And process control block, under the process control, so this is the actual data structure of XV6 kernel, which is a toy operating system that mimics Unix. And whenever a process is created, it also creates one object of the proc to represent that process. 그 프로세스가 만들어졌다고 하면 실제로 그게 OS에서도 표현이 돼야 되잖아요. 그게 어떻게 표현되냐면은 이 proc 스트럭처 하나 만드는 거예요. 그러니까 proc 오브젝트를 하나 만드는 거예요. By allocating a new object of the proc, we can actually create a process in kernel. And aspect, let's see the aspect of the proc. First one is what? Pointer to process memory. How it is actually implemented, don't care at this moment. But just assume that it points to a starting location of the memory space that this process is given. Complicated stuff, but we will see the detail later part in this course. Anyway, one thing you need to check is that, okay, it is given a certain amount of the memory space, so it have an address for that. And also it indicates amount of the size of the memory that is given. And also kernel stack is a bit complicated stuff, but under this, inside of this program execution, sometimes it invokes a kernel facility. So as a similar that application program have a stack, inside of the kernel also have some stack. So it also This is a pointer that indicates the point of the kernel stack that's relevant to this program execution. Okay, so these are, you can think of them as kind of a attribute for representing memory space of an application program. And now here's come is process states. The first thing is that enumeration of the proc state and their state. And what are the proc state? Proc states are defined in here. Unused, embryo, sleeping, runnable, running, zombie. And you can think, I'm not quite sure about them, but I think unused and embryo can be mapped to the new state when it is just created. Sleeping is, you can think of it as a blocking, blocked. Runnable means ready. Running means running. Zombie means zombie. Zombie means zombie. Okay? So a process belongs to one of these threads. So these states. So this one indicate in which state the current this process is currently reside. And then PID, yeah. And then it have a pointer to its parent. And then what's this one? Sleeping on channel. I'm not quite sure about this one. And also this is kind of a flag, I guess. And what here comes is a list of the file that the current process opens and hold in kernel space. These are pointer to the file resources. How they are managed, please wait, and we will see in detail. But there are some context related to the files. And then what? Here we have a context. And what this context is, these are actually snapshot of the CPU. And these are what? Actually name of the register. Yeah. So actual value that is stored in the register will be copied to here when context switching happens. So as we just restore all this register value back to the CPU, then execution will continue from the stop the moment. Okay. So this is actual process control block in the x86 kernel. So I told you about basic mechanism of time sharing so far, but I don't tell you about these remaining issues. So we have many remaining issues. First thing is that, okay, I see that how CPU can be virtualized by time sharing, by context switching, but what's overhead for this one? I mean, if we don't have a time sharing, then for 100% of time can be used for executing application program. But by having time sharing, we need to time execute context switching. So it brings up some overhead because decent amount of time will be used simply for managing the time sharing, not for making a progress of the program, right? This is a really important issue. So this should be as minimal as possible, which means that context switching and scheduling must be very quickly done. So we cannot bring heavy logic here. The context switching and scheduling must be simple as possible. Otherwise, it'll bring up so much overhead and later it hurt the performance of the total system. And also how to implement context switching. Okay, I see how context switching can be happen, but how can we regain the control back from the currently running process? I mean, currently running process determine which execution to execute next. That's how control flow goes. But how can we regain the execution back from the currently running one? By how? CPU에서 한번 딱 돌리기 시작하면 어떻게 돼요? CPU가 알아서 계속 돌리죠. 근데 그걸 막을 수 있는 방법이 있어요? 한 가지 있습니다. 여러분 이미 배웠어요. There are one mechanism that creates another context from running one. What? Interrupt. When CPU got interrupted, then the fetching doesn't happen by PC, but fetching happen according to the interrupt handler. So we will see how to use the interrupt mechanism for implementing context switching in next class. And also how multiple processes are managed. I briefly told you about this one, but there are many details and complicated things regarding this one as well. And last piece is that, okay, I kind of catch how context switching happened, but how scheduler will determine which process, which ready process to execute in next time, and what kind of algorithm are there, and what kind of pros and cons scheduling algorithm has. We have a lot of things to discuss, and I will continue this discussion in the coming Friday class.